Hello students, in my previous video I've explained reflection of light. I told you about spherical mirrors. I explained the image formation in case of concave and convex mirrors. Let me start today's lecture by showing one experiment based on reflection of light. For this I've taken one plane mirror, I've taken one glass slab and I've taken one protector, and I have drawn two lines which are perpendicular to each other. Now I place the protector exactly on the mark where the lines intersected. Here I kept the protector and here I am going to keep the slab, and in the back side I am going to place the mirror. Okay, so I kept the mirror here, I kept glass slab in front of it and the protector just to find the angle of incidence and angle of reflection. For the ray of light I am using one laser pen. Now I am starting the experiment. I am passing the light from a laser pen. Now you can see this is the incident ray, this is the reflected ray, and already I have drawn one perpendicular which is normal. Now you can see here incident ray, reflected ray and normal all lie in the same plane. As I told you in my previous lecture when I explained laws of reflection, that incident ray, reflected ray and normal all lie in the same plane. And second law, I told you that angle of incidence equal to angle of reflection. This is the incident ray, this is the normal, so this angle is the angle of incidence. This is the reflected ray, so this is the angle of reflection. Here this angle you can see 10, 20, 30, 40, around 40 degree is the angle of incidence. Here also it is 10, 20, 30, 40. So here angle of incidence also 40 degree, angle of reflection also 40 degree. So from this experiment we learn two things: incident ray, reflected ray and normal all lie in the same plane, in the plane of paper, and angle of incidence, which is approximately 40 degree, is equal to the angle of reflection, which is also 40 degree. Let me show you another experiment. Now I am showing you the second experiment. For this I am using one laser pen and one glass slab. Now initially we are passing a ray of light through this point, and this ray of light moves in a straight line path because it is moving in air, which is also known as rectilinear propagation of light. I told you in the properties of light that ray of light always moves in a straight line path. If I keep the glass slab in between, you will find that ray has changed its direction. Initially it was here, and now it has shifted. Here air is present, here glass. So when ray of light moves from air to glass, it has changed its direction. This bending of light or change in the direction of light when a ray of light moves from one optical medium to another optical medium is known as refraction of light. I hope what is refraction of light is now clear. Let me give you another example. For this I have taken one glass, I have taken a spoon and water. Now in this glass, if I keep a spoon, you can see the spoon is now straight. Now if I pour water slowly in this glass, you just see what happens. Just see, now it appears as if it is now bent. It seems to be a magic. Just see, up to this much it is straight, and as if it has broken from this part, and now you can see this part separately. Once I keep it inside water, it appears to be broken. This is because of one physical phenomenon which is known as refraction of light, and in today's lecture I am going to explain this phenomenon only. Hello students, I hope you have liked the practical demonstration of reflection and refraction of light. In my previous video I have explained reflection of light, and I told you about image formation in spherical mirrors. And today I am going to start refraction of light. Now before starting refraction of light, let me explain some basic terms which are related to refraction of light. First of all, what is a medium? Medium means a transparent substance in which light travels is known as a medium. You can consider a piece of glass. A piece of glass, through this light can pass easily. If you take water, through this water also you can say light can pass very easily. So glass, water, air, vacuum, all these are medium. Now speed of light in vacuum is 3 into 10 to the power 8 meters per second. But the speed of light is not same in all the cases like air, glass, water, alcohol. The speed of light varies while moving from one medium to another medium. In vacuum it is maximum, which is 3 into 10 to the power 8 meters per second. In air, it is marginally less, but for practical purposes, we always consider 3 into 10 to the power 8 meters per second. In case of glass, it is approximately 2 into 10 to the power 8 because it depends on the type of glass. And in clear water, it is around 2.25 into 10 to the power 8 meters per second. In this way, the speed of light is different in different media. And why it is so? Speed of light depends on the optical density of the medium. Optical density, which is different from normal density. It is different for different media, and the optical density of a medium is calculated in terms of speed of light. If we compare the speed of light between air and glass or glass and water, then only we can get the idea about optical density. Now, in case of optical density, we can use two terms here. One is called optically rarer medium, another is optically denser medium. Now, in case of optically rarer medium, we say a medium in which the speed of light is more. If we compare the speed of light in suppose air and glass, you can see the speed of light is more in case of air as compared to glass. That means air is a rarer medium as compared to glass. Out of these three, maximum speed of light is in air as compared to glass and water. So air is optically rarer as compared to glass and water. And what is optically denser medium? A medium in which the speed of light is less is called optically denser medium. So if I consider suppose glass and air, out of these two, the speed of light in glass is less as compared to air. Since speed of light in glass is less as compared to air, so glass is optically denser. Now if I compare glass and water, in case of glass, speed of light is 2 into 10 to the power 8. And in water, it is 2.25. So out of these two, in glass, the speed of light is less. So glass is optically denser as compared to water. So in case of optical density, always we have to compare the speed of light in two media, and then only we can say whether it is optically rarer or optically denser medium. Now what is refraction of light? Already I have given you practical demonstration. Now you can see when a ray of light moves in one transparent medium, when it enters another transparent medium of different optical densities, then it deviates from its path. You can see here this ray is moving in air. Once it entered in water, it cannot move in the previous direction. It will deviate from its original path. This phenomenon is called refraction of light. Definition wise, we can say the phenomenon due to which a ray of light deviates from its path at the surface of separation of two media when the ray of light is traveling from one optical medium to another optical medium is called refraction of light. Now here you can see this is a ray of light which is moving in air, and this ray is striking the boundary between air and water obliquely. So it is moving from an optically rarer medium to an optically denser medium. Now this ray of light, once it will strike the boundary separating two media, this ray will change its direction and it will go in a different path. This ray of light is supposed to go this way, but instead of going straight, it will deviate towards the normal. This bending of light when a ray of light moves from one transparent medium to another optical medium of different densities is known as refraction of light. Now one thing you have to keep in mind that no refraction of light takes place if a beam of light or a ray of light strikes another optical medium at right angles. Here you can see the angle is 90 degrees. So in that case, ray will pass straight without causing any type of refraction. Suppose this is a ray which is striking the boundary separating two media, then this ray is called incident ray. When this type of ray strikes the surface, then a part of it is reflected and a part of it is refracted. After striking, this ray will change its direction. As you can see, it is supposed to go this way, but now it is going this way. This ray is called the refracted ray. So this one is incident ray, this one is refracted ray. If I draw one perpendicular here at the surface, then this line is called normal and this point is called the point of incidence. Angle between incident ray and the normal is called angle of incidence, and the angle between the refracted ray and the normal is called the angle of refraction. Now, when a ray of light strikes at right angles, in that case, incident ray and normal, both of them are in the same direction. So in that case, angle of incidence will be 0 and angle of refraction also will be 0, because we know no refraction of light takes place if a ray of light strikes another optical medium at right angles. So this ray will go straight without causing any refraction. Here you can see one ray of light is moving from air to glass. As you know, the speed of light is more in air as compared to glass. That means the ray is moving from optically rarer medium to an optically denser medium. This ray, after striking the boundary, it will bend towards the normal. As you can see, this is the normal, this dotted line is the normal. So this ray of light, instead of moving straight, it will bend towards the normal. So when a ray of light travels from optically rarer medium to an optically denser medium, it bends towards the normal. And if you see angle of incidence and angle of refraction, here angle of incidence will be always more as compared to the angle of refraction. And when a ray of light moves from optically denser to an optically rarer medium, here it is going from glass to air, the speed of light in glass is less and speed of light in air is more. When a ray of light moves from an optically denser medium to an optically rarer medium, ray of light will bend away from the normal, and here angle of refraction will be more than angle of incidence. So now we can say when a ray of light travels from a rarer medium to a denser medium, it bends towards the normal at the point of incidence, and here angle of incidence will be more than angle of refraction, as you can see here. And when a ray of light travels from a denser medium to a rarer medium, it bends away from the normal. In that case, angle of refraction will be more than angle of incidence, as you can see in this figure. Suppose a ray of light is passing through a rectangular glass slab. This ray of light is moving in air. This part is glass, this part is again air. Since it is moving from an optically rarer medium to an optically denser medium, this ray of light will bend towards the normal. So this ray will start moving in this particular direction. Now the ray is moving from glass to air. That means it is moving from optically denser medium to an optically rarer medium. So this ray will go away from the normal. Now this ray is called incident ray, this is refracted ray, and this is emergent ray. Now this is the actual direction of incident ray and this is emergent ray. The perpendicular distance between direction of incident ray and the emergent ray is called lateral displacement. The perpendicular distance between this direction of incident ray and the emergent ray is called lateral displacement. Now definition wise we can say the perpendicular shift in the path of incident ray while emerging out of a rectangular optical slab is called lateral displacement. Now in this figure, ray of light is moving from air to glass and then glass to air. This ray of light is going from air to glass, so it is moving from an optically rarer medium to an optically denser medium. So this ray, instead of going straight, it will bend towards the normal. And here the ray is going from glass to air, that means from an optically denser medium to an optically rarer medium, so it will go away from the normal. Now the perpendicular distance between direction of incident ray and the emergent ray is called lateral displacement. Now this lateral displacement, it increases with the increase in the angle of incidence. This angle is the angle of incidence, more is the angle of incidence, more will be the lateral displacement. It depends on the thickness of the slab. More the thickness, more will be the lateral displacement, and it depends on the optical density of the slab. So these are the three factors which increases the lateral displacement. Laws of refraction. So according to the first law of refraction, incident ray, refracted ray and normal at the point of incidence all lie in the same plane. This law is similar to first law of reflection. Now this angle is called angle of incidence and this angle is called angle of refraction. Now according to the second law of refraction, which is also known as Snell's law, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for the light of a given color and for a given pair of media. So sin I by sin R, if I divide, I am going to get a fixed value, and that value is known as the refractive index of the second medium with respect to the first medium. In trigonometry, you have done sine theta. So if you take sine of the angle of incidence to the sine of the angle of refraction, that ratio will be a constant. And that constant is called the refractive index of second medium with respect to the first medium. This law is also known as Snell's law after the name of the scientist W. Snell. Now, what is refractive index? The ratio between the sine of the angle of incidence in one optical medium to the sine of the angle of refraction in another optical medium is called refractive index of second medium with respect to the first medium. So it is generally represented by the symbol n or mu. It's a Greek alphabet. Suppose a ray of light is moving from medium 1 to medium 2. Then according to Snell's law, we can write sine of the angle of incidence to the sine of the angle of refraction equals to 1 and 2. That means it is refractive index of second medium with respect to first medium. It can be also written as n12 or it can be written like mu12. These are different ways of writing refractive index. Now here ray of light is moving from medium 1 to medium 2. So here you see first we are writing medium 1, medium 2. Medium 1, medium 2, here also medium 1, medium 2. Here a ray of light is moving from glass to air. This is the angle of incidence and this is the angle of refraction. So here sin I by sin r is the refractive index of air with respect to glass, which can be written this way or this way. Now suppose a ray of light is traveling through vacuum or air and is then refracted in another medium. Then ratio of sin I by sin r is termed as absolute refractive index of that medium. Definition wise, we say if the incident ray is traveling through vacuum or air and is then refracted in a medium, then the ratio sin I by sin r is called the absolute refractive index of that medium. Absolute refractive index can be expressed in terms of speed of light also. So absolute refractive index of a medium is defined as the ratio of the speed of light in air or vacuum to the speed of light in that medium. So we can write absolute refractive index is speed of light in vacuum or air to the speed of light in a given optical medium. Okay, say for instance, in case of diamond, the ratio between speed of light in vacuum or air to the speed of light in diamond. So whenever we have to calculate absolute refractive index, always take the ratio of speed of light in vacuum or air to the speed of light in that given optical medium. When a ray of light moves from one optical medium to another optical medium, the frequency of the light remains same. So whatever is the frequency here also frequency remains same, but the speed of light and the wavelength of light here and here will be different. Clear? During refraction of light, the frequency of light here and the frequency of light in the other media remains same, but the speed of light and the wavelength of light here and in the other media, it will change. Now we know the speed of light in a medium is wavelength of light into its frequency. Already I told you that absolute refractive index is the speed of light in air or vacuum to the speed of light in that medium. Now since speed of light is wavelength into frequency, so we can write wavelength of light in vacuum by wavelength of light in optical medium into their frequency. And as frequency remains same, so these two values will be same, these two values will be different, so we can cancel these two, so we are left with wavelength of light in vacuum by the wavelength of light in optical medium. So absolute refractive index of a medium can also be defined as the ratio of wavelength of light in vacuum to the wavelength of light in that particular optical medium. Now suppose this is a container containing water and this is one point. From this point rays are going in different direction. Suppose we have considered these two rays, and these two rays while going from water to air, they suffer refraction, and since they are going from optically denser to an optically rarer medium, this ray will bend away from the normal. When these rays strike our eyes, it appears as if the rays are coming from this point. So image of this point will be formed here. So whenever we stand near a swimming pool, it appears to be less depth because of the same phenomenon. Here, this is the apparent depth and this is the actual depth. Now, if you want to find absolute refractive index, real thickness by the apparent depth, this ratio also gives absolute refractive index. In case of refractive index or absolute refractive index, since it's a ratio, it cannot have any unit. You take a metallic vessel and place a coin at the bottom of the container. Now slowly move away from the vessel until you reach a place where the coin just disappears. Now you can ask someone to slowly fill the vessel with water without disturbing the position of the coin. Slowly you will find that the coin gradually begins to appear and can be seen completely from the same position of the eye after the level of water rises up to a certain level. It is because the rays of light which were going straight, now they are going to bend away from the normal, and as a result the coin will be visible. It will appear slightly higher than its actual position. And this technique is often used in magic shows when they take one container and claim nothing is there. Then after saying two mantras they pour some liquid and the coin or some object becomes visible. Actually all these are because of refraction of light. I hope refraction of light is now clear. And that's all for today. In the next video I am going to explain lens and the types of lens. Till then, bye bye, take care and wait for the next video.